This conference will now be recorded.
So very good evening, students. Today we are back with the discussion of magnetics part, where basically we'll be discussing about the questions, previous year's questions from JEE Advanced paper on magnetism. This magnetism includes even the induction part also. So here it will be, so this sixth chapter also, EM induction also, EMI, EM induction. So chapter 6 also would be included here. Okay, so let us start our discussions for today. So look, this question, this is really very interesting question. A charged particle that can be electron or a proton is introduced at the origin. So something like this. So at the origin the particle is there. Let us say this is Z, this is Y, and this is X direction. Okay, so kind of that. And the particle is introduced with a given initial velocity v, a uniform electric field E, and magnetic field B are given in column 1, 2, and 3 respectively. The quantities E0, B0 are positive in magnitude. So see, there are 3 columns, 1, 2, and 3. And first column, the charged particle and the corresponding velocity vector is given. Suppose in this case, first one is electron, which is introduced with a velocity 2 E0 by B0 x cap, and the electron with velocity E0 by B0 y cap, then proton B0 V velocity is 0, and fourth also proton, particle proton, which is given a velocity V is equal to 2 E0 by B0 along the x direction. Okay, and in the column you see this is like here the electric fields are given, and in the column 3 magnetic fields are given, and you can see this is along z direction with magnitude E naught square. Here it is negative y direction with magnitude E0. This is negative x direction with E0, etc. And similarly magnetic fields are also given in various directions. So we will have 3 questions related to this table, which we have to match. Suppose I have to match with this column, and this column. Look this question. So in which case the particle move in a straight line with a constant velocity? In which case the particle moves in a straight line with constant velocity? So this question, how do you answer this question? Look here the options. Option is column, see this 2 representing the electric field with the particle. So this is particle electron, and with given a velocity E0 by B0, right? And see this thing, electric field. So look there, see this is from first column, this is from second column, this is from third column. That means you have to choose what velocity along which direction you have to provide, and what will be the electric field direction and magnitude, and what will be the magnetic field direction and magnitude. That you have to choose from these 3 columns. See in first column, see this is Roman numbers 1, 2, 3, 4, and here it is 1, 2, 3, 4. These are like in the capital Roman, and this is small Roman, and this is PQRS. So here if you look the options, so these are matched. Okay, these are the options where combinations of these 3 V, E, and B are given. We'll just now see the options one by one. So the first option is 2. We'll write it here, 2, 3 and S. Okay, 2, 3 and S. Look, this first option says this, this and this. Sorry, S. These will be matching. Okay, so first option says that. So what was the question? Question was, in which case the particle will move in a straight line. See, if a particle has to, see, this is obviously uh, the particle, the charge, if charge particle moves with the velocity in the region where there are both electric and magnetic fields, then it will experience Lorentz force. As you know, Lorentz force is given by the charge into whole into E plus V vector cross B vector, B cross B. So Q into E plus V cross B. So this is the formula, and see, the charged particle will move in a straight line with a constant velocity. That means what? This happens only when this Lorentz force will be 0. That means a particle, you know, like a particle, this is Newton's first law, right? So if there is no external force acting on an object, so it will move with a constant velocity in a straight line, right? So that is the thing. So external force on the charged particle has to be 0. Then only that will happen. Okay. So a particle will move in a straight line with a constant velocity only when the Lorentz force, this will be 0. Now we have to check for which combination the Lorentz force is going to be 0. Look, the first option itself. We'll just write the force over here. See, first option says 2, 3 and this. See, obviously here, see this thing, charged particle is electron, right? Charged particle is electron. So if the charged particle is electron, then the force, electric force, will be along y direction. So this will be electric force. And what is the electric force? Electric force will be, so this multiplied with this, right? So in this case, electric force is E0 square by B0. I'm sorry, no, this is Q into E, right? So Q into E, that means electronic see, this will be along y cap direction, okay, along y direction. Now this is the electric force, then magnetic force has to be V cross B, E0 by B0. See, this is B0 and it is Y cross Z. See, I know X cap, Y cap and Z cap. So YZ will give you X cap, right? In this case, I'm sorry, this electric field is along X cap, along X cap. So this force is along X cap. See, this will give you positive X cap, but the particle is negative. negatively charged, so here it will be negative. Therefore, look, this b0 will go away. This is e0 e to the power. Here e will be there. E is 0. This is along x cap, and this is, see, yz will give you positive x cap, so it will give you ultimately x cap. So this will give you 0. So this is our Lorentz force. So we get Lorentz force to be 0. It is a null vector. So Lorentz force is becoming 0 for this combination, first combination itself. Okay, for the first combination itself. So the first combination is giving you Lorentz force 0. Now we'll check, just for cross checking, any other combination whether it is giving 0. Let us check this D 3,3p. 3,3p. We'll just take 3,3p. 3, 3 and p. Let us see. If the velocity is 0, the magnetic force will be 0. Magnetic force will be 0. Electric force will be there. It is along minus x cap. Okay, it will be minus x cap. But here, since there will be a force acting on this particle proton, even though it has initially 0 velocity, because of the electric force, it will have some acceleration, and at the same time it will have a velocity which is varying velocity. So this constant velocity, the question was there that the velocity will be constant. Okay, see, it is moving along x-axis. It is a straight line, that is fine. Along minus x-axis, that is very fine in this case, for this option, because electric field, so if it is proton, so it will be moving along negative x direction, that is fine, moving along straight line. But it is not with the constant velocity, because it is getting experienced, like it is actually acted upon by an electric force. So force is there, means there will be acceleration. So for the velocity will not be constant. Let us take another option here itself. If we take C, 3 to R, 3 to R. Let us go with 3 to R. 3 to R. Sorry, R. 3 to R combination. So in this case also, see, velocity is 0. So charge particle will move in the negative y direction, that is fine. But it is acting like it is acted upon by an electric force. So there will be acceleration, and then there will be no constant force. Okay, sorry, constant velocity. That's why the most appropriate is the option 1. Okay, all right, we'll go to the next question related to this table itself. In which case the particle describes a helical path along positive z direction. Positive z direction. See, first of all, I'll tell you one thing here. Suppose this is z direction, this is y, this is x. So you can have helical path in two ways. If you have a velocity of a charged particle making an angle with this theta, so there will be parallel component, and there will be perpendicular component of the velocity. That's how you can get. But in this case, we have to see how the velocities are given along a particular direction. You look, velocities are given along a particular direction, either x or minus, like either x or y direction. Okay, so that we'll see. So helical path can be possible. Helical path can be possible if the magnetic force and with axis z direction. See, this has to be like this. Helical path will be like this. Okay, just like this. it is possible only when, see, the electric field is along z direction, so that it will be pushed along the x direction, sorry, z direction. See, helical means, like magnetic force. If the magnetic force and the velocity, sorry, magnetic field and the velocity, they are perpendicular to each other, then the charged particle entering into this, like entering into the region where the magnetic field is perpendicular to the velocity, so the magnetic force will actually be such that it will make the particle move in a circular path, right? So it is the magnetic force, which is responsible for circular motion. And see, if the charged particle is acted upon by two forces, one is electric force, another one is magnetic force, in such a way that the magnetic force is actually making it to have a circular motion like this, but at the same time electric field is just pushing it along the z direction. Okay, this is the z direction, it is pushing forward. So by the time it completes this circle, it is pushed, so that's how the helical will come like this. Okay, helical will come like this, so it will go forward as well as it will have circular motion. So therefore the electric force must be along the positive x direction, positive z direction. So that's the way to find out the options. Look here, we'll see uh, for which case the electric force will be along positive z direction. So electric force has to be along the positive z direction. So if we take first of all, let us take proton. See, if I take see, these are the electric forces, right? These are the electric forces. So electric force has to be along the z direction. And see, if I take this magnetic field to be along the z direction, right, z direction, so it has to have, see, magnetic force. This has to be, as I showed here. See, if I see this, this is going like this. So the magnetic force has to be in the positive x direction. So negative x direction, okay? Has to be negative x direction. Obviously, it will change the. So okay, let us see the options here. Helical path, right? So first option, 2 and 2 and r, 2 to r. Let us see 2 to r combination. 2 to r. See, in this case, first of all, this velocity of the electron and magnetic force, sorry, magnetic field, they are in the same direction, so there will be no magnetic force, so there will be no possibility of helical path. So first option is rejected. The second option, what is the second option? Second option says 4 to r. Let us see what is 4 to r. 4 2 and r. 4 2 and r. This is 4, here it is 2 and r. So let us just wrap these things. Okay, 4 to R. Look here, this is along x direction, R is along y. Okay, so we'll get x, y. This will be z cap. That is fine. It is moving along z cap. The magnetic field force is along the z cap. Then, okay, another point is that this is along x direction, right? Electric field is along y direction. Okay, so electric field, if electric field is along y direction, then the helical path will not have axis along positive direction. Okay, this is proton, so it will move actually it will move forward in the negative y direction, not along z direction. That's why this option also will not be correct. Okay, second option is not correct. Third option, let us see. So third option says 4-1s. Sorry, 4-1 and s. 4, let us clean everything. 4-1 and s. Look at here. See, electric field is along z direction. Now you see, this is electric field along z direction. If the electric field is along a z direction, then the electric force will be pushing the particle along z direction. That is for sure. Now see, this is V is how much? Along x direction. V is along x direction and magnetic force is along z direction. So xz will give you minus y cap. Let me check here. See, y cap is the minus y cap is down. So magnetic force will be in such a way that it will actually curl in this direction. See, it has to be in the yz plane, isn't it? So helical will be in the yz plane. So z anyway, along z direction there will be electric force. So magnetic force has to be in the negative y direction is fine. Positive y direction also fine. So it is actually, I think this is the correct option. Let me check with the last option also. So this will be, I think this will be the correct option here. I have explained why, because the electric force has to be along the direction of positive z direction, so that it will be pushed along the z axis, and the helical also will have the z axis. Last option is this one. So what is this? D. It is 3, 3 and P. Let us see. 3, 3 and P. 3, okay, clean us. Okay, so 3, 3 and P. Okay, so this is C. Electric force will be in the negative y direction, and there will be no magnetic force since the velocity is 0. So there is no way of having, or no chance of having, helical path at all. Okay, so the last option also not correct. So look, then the option 3 will be, or option C will be the correct option for this case. Okay, we'll go to the next question related to the same table. In which case would the particle move in a straight line along the negative y direction? Okay, in the negative y direction, how the charged particle will move in a straight line along negative y direction? Let us see the options. First option is 4 to s. 4 to s. See, 4, 2 and s. See this x and z. X and z, see velocity, this will give you x cross z cap. So zx, so this will give you minus y direction. So see, the magnetic force is along minus y direction. And what about this? This is along negative y direction. So this can be this can be an answer. So let us see. We have taken first option 4 2 4 2 4 is this is 2 4 2 and s is c, this is zx, so it will be y, xz minus y, that is fine. Okay, let us see with this thing. 4 2 2 is the electric force is this along the, it will be along. Okay, we can just go with this thing. The magnetic force, sorry, velocity is in this direction. Okay, and magnetic force is magnetic field is along this direction. So magnetic force, see, if this is the velocity along x direction is the velocity, okay, it will be experiencing two forces. One is along, see this, let us just calculate this. So it is electric force will be 2 square 2 E0 square by V0 along minus y direction. Okay, fine. And what about this force? This will be only 2 E0, only 2 E0. Yes, 2 E0 along zx, xz means minus y cap. Fine. So you can see there will be a resultant of these two forces, obviously, resultant of these two forces, and that will lead to negative direction. Okay, let me check with the other options as well. So this seems to be correct. Let us see with the other options. So 3 2 and p, 3 2 p, we need to check with 3 2 p. Three 3 2 and p, 2 and p is this. So in this case, since there is no velocity, so this will not be there anyway, and it it is, see, it will have no velocity, but there will be force along negative y direction. That is fine. So what was the question? Particle describe. Okay, particle moves to the in which case the particle move along straight line along the negative direction of y. That is more along negative y. Okay, more along negative y. So which has more value along negative y. Okay, so we'll see the other option. Let us check with this, because in the answer given by the board is this one. Let us check with 3 2 and r. 3 2 and r. 3 2 and r. Sorry. 3 2 and r. See, in this case there is no magnetic force, right? No magnetic force. So it will be along, see, it will be having a force, electric force, purely in the negative y direction, and that is E0. Magnitude of the force is E0, right? E0. All right, let us look other forces. See, other cases also it is showing negative y direction, no doubt about it, but more negative, it is said more along negative y direction. See, we'll, if we take this can be taken, no problem. We'll see with this C and other options. Okay, other options. The option says, I'll tell you what are the options. Option C says 2, 2. Option C says it is 2, 3 and Q. 2, 3 and Q. 2, 3 and Q. 3 and Q. In this case, 2, 3 and Q, this is Y. See, this is Y. This is electron. So magnetic force will be E0, fine, E0 with the minus sign, E0 into E. Okay, and this Y and this X. If you take cross product, YX, X, Y and Z. So YX will give you minus Z cap direction. Okay. So this is the option C, 2, 3 and Q. So this is not actually giving you this thing, negative Y direction. Okay. So the option C, I don't know whether I have taken the option wrong from somewhere. Okay, C option is 2, 3 Q, 2, 3 and Q. 2, 3 Q, as I said, 2, it is 3 from here and Q from here. So this is the Y cross X, that means minus Z. So this is not leading you to, so one is giving you minus Z direction. Okay, another one is giving you minus Y direction. So it will resultant this way. Okay. All right, so it is not the option. Let us see the option B, that is 3 to P. Once more, 3 to P, 3, 2 and P. So in this case, magnetic, no magnetic force, but it is along negative Y direction. Okay, along negative Y direction, that is fine, because this force is not like magnetic, like velocity is not there. So this can be taken. Okay. Okay, so okay, we'll clarify this again. We'll move on to the next problem. So I think for the time being, we'll just fix to this option. Okay. All right, we'll go to the next problem. So this problem is again interesting. You can see there is a circular insulated copper wire. Insulated copper wire loop is twisted. So there was a loop like this. Then it is actually twisted to make this. Okay, one is twisted in such a way that one has area greater than the other. Okay, one has the area greater than the other. Okay, this is how it is made. Okay, so this is insulated copper wire. To form two loops of area A and 2A, one has area double the other. So this has 2A, this is A, as shown in the figure, as you see here. At the point of crossing, the wire remains electrically insulated from each other. So at this point, uh, the direction of electric current will be such that, so suppose the current is in this direction this way, and this is in this, like in the opposite direction. Okay, somehow. So that's how actually, uh, so it is like this, and see, it has to be here it will be like this, such that, and in this case also, if I take this to be this direction, then, and this has to be in this direction, so they will actually cancel each other, such that the crossing point will be electrically neutral. The entire loop, like I'm sorry, not electrically neutral, they will be actually remaining insulated from each other, these two loops. Okay, they will not neither attract or repel each other. Okay, so the entire loop lies in the plane of the paper. It is lies on the plane of the paper. A uniform magnetic field B points into the plane of the paper, as you see the cross marks. A uniform magnetic field B points into the plane of the paper. So uniform magnetic field. This magnetic field is uniform magnetic field. Everywhere the magnitude of the magnetic field is same. Intensity of the field is same. At t is equal to 0, the loop starts rotating about the common diameter as axis. As you see, this is the common diameter which is taken as axis, and it is rotated with a constant angular velocity omega, as you see here. Okay, so the magnetic field, in the magnetic field, okay, so which of the following option is, or options are correct given here? Okay, we'll check that. I'll just restate the problem. See, problem is saying that there was a single loop of copper wire, insulated copper wire, and that is actually twisted to make two loops. One is having area A, another one has area 2A, and they are such that they are actually, so these loops are actually electrically disconnected, or they are not related to each other electrically, insulated to each other. The entire loop lies in the plane of the paper. Magnetic field is perpendicular to the plane of the paper and getting into the plane of the paper. Okay, and the loop starts rotating about the common diameter of the both the loops here, and it is, you can just think of that magnetic field, it is lying on the plane of the paper, and magnetic field is into the plane of the paper, and it is rotating vertically. You can just think that it is rotating vertically in the vertical plane. So during the rotation there will be change in the flux, that is for sure. Okay, so that is one point. Let us see the options. The rate of change of flux is maximum when the plane of the loop is perpendicular to the plane of the paper. We have to see the rate of change of the flux, maximum flux. Okay, rate of change of flux means EMF, that we have to understand. EMF induced. The net EMF induced due to both the loops is proportional to cos omega t. We will see that. The EMF induced in the loop is proportional to the sum of this, actually sum of the areas of the two loops. Okay, then the amplitude of the maximum net EMF induced due to both the loops is equal to the amplitude of the maximum EMF induced in the smaller loop alone. So that we have to justify which one is correct answer for this question. So first of all, this is a question related to magnetic flux alone, magnetic flux and induced EMF. I'll just tell you a basic point. Suppose you have a circular loop like this. Let us see. You have a circular loop like this, and it is in the magnetic field. Similar thing as you see in your problem. I'm just telling you with a single loop. When you have a single loop like this, and this loop is rotated about its diameter, about its diameter with certain angular speed or angular velocity. Suppose this is the common diameter, angular velocity omega. With omega it is rotated. So in this case, induced EMF, how to find out induced EMF? First of all, how do you find out, or how to write down the flux? See, suppose the loop has, I have expression for flux to be B dot A, right? Or we can write BA N cap and B cap. Sorry, this will be dot. BA, these are the magnitude of the fields and the area, and N cap is the, okay, I'll write in the reverse order. B cap and N cap. B cap and N cap. This N cap is the area normal, and B cap is the direction of the magnetic field. If the angle is theta and it is rotated about this diameter with angular velocity omega, then this theta can be written as omega into t. Okay, so look here, this I can write either BA cos of theta or phi is equal to BA cos of omega t, right? So this is the expression for the flux. Now we have to see for both the thing. Let us see, the first option is the rate of change of the flux is maximum when the plane of the loop is perpendicular to the plane of the paper. We'll see that whether it is true. Okay, so we have seen that if this is the case, this is N cap, this is B cap, and this is theta, and it has area A, and if it is moving with velocity v, after time t, what will be the flux? The flux will be BA cos of omega t, right? It is with a single loop. It is with single loop area with this, and another one. See, the first option is rate of change of maximum. The change of flux is maximum. We have to see the change of flux. First of all, let us write the flux itself. So this is phi 1. What about phi 2? So phi 2 will be BA. It is 2A, just 2A and cos omega t, because both are moving along the same direction and with the same velocity, about the same axis of rotation. So this is the flux. So 2BA cos of omega t, right? 2BA cos of omega t. And so what will be the total flux? So total flux could be 3BA I'm sorry, this we have to see how it is the total flux, how the total flux will be. See, as I was telling you, in this case, according to the question, both will be electrically insulated from each other. That means the current direction in the first case, okay, current direction in the first case will be opposite to the direction, current direction uh, in this case. Okay, all right. So therefore, the magnitude of the net flux, magnitude of the net flux will be 2BA cos omega t minus BA cos of omega t. Okay, so this will give you BA cos of omega t. Okay, this is the net flux induced in both the loop. Okay, now if we know the total flux, if we know the net flux, then net induced EMF will be minus d phi net by dt. Okay, so this will be, say, BA and cos omega t, ddt of cos of omega t. What it gives? Cos omega t is minus sin omega t with with omega multiplied here. So this will be, the flux, sorry, induced EMF. So if this is the induced EMF, so induced EMF is actually the rate of change. So the question was the rate of change of the flux is maximum when the plane of the paper, sorry, plane of the lobe. See, this omega t can be taken as theta, as I said. So it is actually BA omega cos, sorry, sine of theta. So this is the flux, sorry, induced EMF. Induced EMF, net induced EMF is BA omega sine theta. Okay. Now the rate of change of the flux will be maximum when this theta is 90 degree. Theta is 90 degree. That means, you know, when the magnetic field and the loop perpendicular, like sorry, outward normal of the loop and the magnetic field direction will be perpendicular to each other. At that situation, the induced EMF will be the maximum. The rate of change of, in the option it was there as, excuse me, rate of change of the maximum flux is maximum, sorry, rate of change of flux is maximum when the plane of the loop is perpendicular to the plane of the paper. So plane of the paper means direction of the magnetic field itself. Okay, so this is true. This is the first option is actually correct. Now let us see the net EMF induced due to both the lobes is proportional to cos omega t. Now this is actually proportional to, EMF is proportional to sin omega t, not cos omega t. It is EMF. Flux is this. The net EMF induced in the loop is proportional to the sum of the areas of the two loops. No, this is also not true. We have already calculated, that is BA cos omega t, that is the plus. The amplitude of the maximum net EMF induced due to both the loops is equal to the amplitude of the maximum EMF induced in the smaller loop alone. This is true because this here it will be BA cos of theta, and we have got net value to be the same. What we had got net plus, we had got BA cos of theta, we had got, right, net. And for A also we will get the same thing. For the loop A, so loop A has greater area, smaller area anyway, so this also will be the plus, same plus. So induced EMF, net induced EMF will be actually same as the magnitude of the EMF produced by the loop, smaller loop alone. Okay, that is true. So this D option is also true. So option D was the amplitude of the maximum net EMF induced due to both the loops is equal to the amplitude of the EMF induced in the smaller loop alone. This is true. So we have seen this. I think if we start the new problem, this is also a paragraph related problem. It will take another half an hour to explain this problem alone. So we'll not start new problem today. We'll discuss this question in the next class. Okay. So thank you for your patience. Bye for today.